Today we are watching Angular Momentum, a vector quantity by Modern Learning Aids, published in 1966. So I'm going to be honest, this does not seem like the thing that I would be most interested in, but I am curious. I'm curious what exactly we're talking about here. But I'm more curious about their application of angular momentum. I'm curious to see what examples or what reasons they give for studying angular momentum. Not that I'm too familiar with angular momentum, but I think 1966 angular momentum, we were definitely doing some important physical studies at this time. So maybe I'm hoping maybe we're related to like the space race or something like cool like that. I'm hoping for, but I guess let's just get started. Angular momentum, a vector quantity. The Physical Science Study Committee, with the support of the National Science Foundation, presents as part of its Advanced Topics program in physics. So this is an advanced topic program in physics. So I don't even know if I'm actually going to understand everything in this. So maybe I'll actually do some real school book learning today. Let's see. Again, I think this is saying that this was made for schools. Again, it's tough to tell the purpose for any of these, but it's like, why would you make a program on angular momentum if you're not trying to teach somebody? So this might have been a college though. I don't know if this is like, I don't know if this is like elementary or high school even level. Like angular momentum seems like something a college kid would be learning about. Maybe like a high school senior or something. I don't know. I learned physics in like ninth grade, so maybe not. Dude, I love just like the seconds upon seconds of like empty space and empty noise. Like no music, no narration. We're just cold open and we don't have no clues as to what's happening. We're just watching. I love this sort of stuff. Yeah, like I've been watching this shot of like whatever this tube thing is coming from the ceiling for like 10 seconds and like nothing's happening. I'm hearing this like weird metal like spinning sound, but this would not keep people's attentions nowadays, I guess is what I'm trying to say. Oh wow, we waited that long and then it gave us the title card. We waited like 10 seconds on this shot just for it to become the title card. And I don't even understand what we're looking at here either. Angular momentum, a vector quantity. Aaron Limenick. Yeah, shout out to Aaron Limenick. Okay, that's pretty cool. I should have paused this before and guessed what was going to happen because I knew something was going to happen, obviously, but I didn't know this was going to happen. But I know why. I mean, I remember learning about angular momentum. I know that like if something spins, the momentum goes out like perpendicular to it. So I get what's happening, but to people who didn't know about angular momentum at all, like this must have been almost like a magic trick. Actually, this is like a legitimate magic trick, honestly. Like, like it's not that it involves magic, but it's like this. There is like no other way to explain to a person easily how this ball is levitating. You know? Yeah, I would be shocked if I was watching this. I'd be like, how does it work? I hope somebody watching this now is thinking that, like, oh my god, like, I hope some of you have never encountered angular momentum because you're in for you're in for a treat, I guess. Again, we're like a full minute into this and no one's given like any sort of explanation. But this is a bit of a longer program anyways. So, maybe we're just taking our time. I can only imagine, yeah, if you don't know angular momentum at all, you're probably mad curious at this point. Like, it's probably like drawing it out of you. Like, why? Why is it spinning like this? I don't understand. It's just, I already know the explanation, so I'm not that curious. But it's funny to think that, like, originally, yeah, everyone watching this would have been mesmerized. It's also funny because this is really easy to fake, Like, it's not that hard to just, like, put a stick with a weight on it, and make it spin. I don't know. Yeah, and it's a big thing that spins, and that's what does it, yeah.
You all knew what was in there. A gyroscope. A heavy, symmetric disc, free to rotate about this axle. And now we've named it. But that's all we've done. We certainly haven't explained it. And if we want to go on to understand how it works, we have to learn something about the motion that
Dude, I love these, like, first era like science communicators. Like this really is something to be learned from. It's like how well this guy gives the presentation. Even in today's day and age where like there's so many YouTubers who give like presentations on science and stuff, like, but this guy giving us like a whole lecture in one unedited cut is just impressive. And you don't get science communicators like that very often anymore, who can just go off on an entire like on a whole textbook page of physics and just speak to the camera confidently and competently. This is a lost skill right here. I want us all to appreciate this guy's presentation skills going forward. I hope that doesn't come to bite me because we're only a minute in.
This spinning motion. Before we go on to an explanation though, let me show you the same thing.
Oh man, I thought he was going to cut to the sponsor real quick. I thought that was going to be like, imagine this guy doing like a VPN ad read or something.
With a larger wheel, where it'll be much easier to see.
What really is bizarre is like this does replace a full college lecture. This is what a college professor would like say and perform in front of a lecture hall, you know, like this is no different. We are pretty much attending a college class for the next 20 minutes. Yeah, this is literally what I did in my college physics classroom, was a bicycle wheel, because you spin it. Oh my god, yeah, I did this exact same lesson.
There's nothing special about this connection.
Well, what they do in this lesson is they actually let you hold onto the bike or onto the bike wheel so you can feel it. You know, obviously you have to see it for this, but when you take this lesson for real, you actually get a hands-on lesson.
Connection. 2 thumb screws to hold the bicycle wheel axle, a pivot free to rotate, and a low friction bearing. The observation we have to make is very simple. A wheel which isn't spinning, when released, falls, as it should. However, if the wheel is spinning...
Can he really get it going fast enough to stay there? Like, I feel like you need like a power tool or something to get it going so fast that it would stay. I really want to see him do it with his hands.
It doesn't fall.
No way, that's all it took? I really thought it was going to be way more than that.
But instead, moves about the pivot.
Are you for real? That's crazy. Here I am saying that I already know and understand angular momentum, that I've already been given this demonstration before in real life, but like, I don't know, there's something about seeing it here. That was wild. Like he just gave it like one flick and it's already going off like this.
With a characteristic motion called precession. Let me show you one other thing though. When I first drop the wheel, it does fall a bit and then recovers, and in fact precesses about the pivot with a bobbing motion called nutation.
Yeah, if I had never learned this before, this would be like absolute black magic to me.
We won't be concerned with nutation.
Like even understanding it, I still don't understand it, you know?
Let's watch the precession once again.
Like how does that actually make any sense? You know what? This program is convincing me to not believe in angular momentum anymore. It's reducing my understanding of it. In a good way, obviously. It's making me like curious about it once again, I guess. Like this is jumpstarting my curiosity in something that I already understand, which is a good sign.
Now let's go on with our explanation.
What if you spun it in that position? Would it go all the way back up, or would it just be spinning like that? I think it would just stay if you spun it like that. I don't think it would rise up. But again, that's the counterintuitive nature of angular momentum.
We can consider this wheel to be made of separate particles, each moving in a circle about the axis. Let's fix our attention on one of them. Suppose we consider this particle, for instance. Its mass is m1.
Dude, that's a fantastic M that he just wrote.
Its distance from the axis, r1, and it's moving this way with a velocity v1 perpendicular to this radius vector. We can write its angular momentum. Its angular momentum is L1 equals the linear momentum.
Do you all have your notebooks out? You're ready to take notes on this? All right, just make it sure.
M1 V1 perpendicular.
Dude, does he know how to write the letter M?
Times.
That's one too many loops, my guy.
R1. We can also express this angular momentum of the particle in angular language But to do that, I'll have to rearrange
The finger that he just pointed at the L with, too.
these two factors. Writing this again.
But again, this guy's such a good presenter. Like, he has not looked down or looked for notes or cue cards or anything. Like, he actually knows this physics. And that's what, like, separates him from a normal presenter to, like, a good one.
L1 is equal to M1, R1, V1 perpendicular. The same expressions we had before.
I don't know if I could read this equation at all.
And now if I divide
I wouldn't even know that that's a V.
V1 by R1, and of course
I wouldn't know that's an R either, jeez.
multiply by R1 to keep this expression the same, getting an R1 squared. This expression for the angular momentum breaks into two factors very naturally. The first, what we call the moment of inertia, and the second, the angular velocity of the wheel. So, writing the angular momentum of this particle again, L1 is equal to
You guys are all still taking notes, right? Okay, good.
J1, the letter given to the moment of inertia of the particle, times omega, the angular velocity of the wheel.
That's omega. See, what's, I guess, a lowercase omega?
We've now computed the angular momentum of this particle. We could do the same for one here, or one there, or one here. In fact, for every particle in the wheel. And when we do, we can find the total angular momentum of the wheel by adding all these separate angular momenta together. Let me write the expression for that addition.
That's how you know this guy's a pro. He said momenta instead of momentums.
The total angular momentum of the wheel is equal to L1, the angular momentum for the first particle, plus L2 for another particle, plus L3 for another particle, plus, and so on until we've added all the particles. A more convenient and a shorter way for writing this would be to write L is equal to the total moment of inertia of the wheel, which is the sum of the separate moments of inertia, times omega, the angular velocity of the wheel.
I did not know omega, lowercase omega, was just a W. I'll be honest there. I know that does not pertain to this at all very much, but I'm out here learning all sorts of stuff today.
Notice that the angular momentum is directly proportional to the angular velocity. We now know how to compute the angular momentum of this wheel. But there's something I haven't told you.
Dude, that brief pause before he continues going. He's a pro. He's just I don't know, you have to, when you are a YouTuber, you have to learn to take pauses before the things that you say. But again, this guy, I don't know what communications training he has, but he's doing a really effective job.
This wheel has an angular momentum which you could compute. And if I were careful about the way I spun it, spinning it with the same speed, this would also have an angular momentum, which might be exactly equal to the one we just had. But it's spinning in the opposite direction. Does this make a difference? Yes.
Yeah, I think it does. Oh, I mean, I guess he just said it. But whenever you learn angular momentum in school, they show you this. You do which way the wheel turns, the momentum goes perpendicular to your thumb, or it goes with your thumb, so perpendicular to the circle that's being made. So if it's going this way, then it's going that way.
Yes, it does. Let me show you that it does. Spinning it one way.
I still can't believe it takes one rip of this tire to keep this whole thing up.
And now the other. The precession is different.
Yeah, I feel like that at the very least makes sense. The whole way it all works is kind of still mysterious and magical, but it makes sense that it moves around one way versus the other way, depending on how you spin it. That just makes sense. That's intuitive.
In order to designate these two directions of spin, a right-hand convention is used. The fingers of the right hand follow the...
Dude, I've told you, he's doing the same thing. That's so funny that I learned this in 2010 or whatever, but yeah, we've had this same technique since 1966 and probably way before that. That's just so funny that that same exact lesson.
Around the axle, and the thumb of the right hand points out the direction of an imaginary arrow used to designate this spin. When the wheel is spinning in this direction, the fingers following the particles around the axle, the thumb pointing out the direction of the imaginary arrow, which designates the spin.
All right, so here's my question, right? He's not going to get to it, but this is you know what? I'll save my question for the end. I'll learn as much as I can, and then I'll give you all my question. But just know that there's a big question coming at the end of this video.
Let me use a real arrow to illustrate. When the wheel is spinning as it is now, the arrow goes in this way. On the other hand, when the wheel is spinning in that direction, fingers following the particles, thumb pointing out the direction of the spin, so my arrow had better go here. And again, there's something I haven't told you.
You sly dog, what haven't you told us? It's all fake anyway.
Once I have the wheel spinning and know the magnitude of the angular momentum and even know which way it's spinning, there's still a matter of orientation. This is one. Here's another orientation. And this one, or that one. Does that make a difference?
You know, I do like that he asks you stuff. This is fun. He's making you think as well.
It too does, sometimes.
Again, this guy's just such a pro.
Which I'll show you by using another wheel.
How old is this guy? That's what I want to know. Is he like 40? I don't know. I can't even tell. Dude, but I love how they will just show you him taking the wheel off. Like any modern production would just cut to the next moment when they have the next example already set up. But this, we actually just watched him just take the tire off. This is empty space right here that we're watching. It's just funny. Yeah, like we really need to watch this guy like finagle with the screws and everything. Like you could have cut this.
Here I have a wheel whose orientation I'll be able to change while keeping the wheel at the same distance from the pivot, changing nothing but the orientation. Let me spin the wheel now and release it. The wheel precesses with some nutation.
What was that word? Nutation? Like Newton? Like it has some... Did he say rotation? Because it sounded like he said nutation, which is another word that I've never heard.
Now, carefully. What I'd like to do now is do nothing but change the orientation of the wheel. And I change the orientation of the wheel by 90 degrees, no more. Turn the wheel, changing its orientation with respect
Oh wow, I wasn't expecting that.
to this pivot by 90 degrees. Now watch.
This is going to do like nothing, isn't it?
Now watch. Spin it. Equally hard, I'm sure. And I drop.
Yeah, exactly. Well, because it's pointed differently. I feel like I'm actually learning this, but it's like I already knew that.
So the orientation does make a difference. Now, if we have a spinning wheel, we can compute the magnitude of the angular momentum, and we can designate the direction and orientation of the spin. What we have here very much resembles a vector quantity. Is it a vector quantity? Does it behave like a vector quantity? Let's go to some other wheels and see if it does.
I know what a vector quantity is. Like it has, direction and magnitude, but I don't get the way he's using it. Like obviously it's a vector quantity. I don't know.
What I have here is a single shaft on which are mounted two bicycle wheels.
All right, so this is actually like more complex than the lesson I was given. So this is interesting. I feel like, again, that's part of why I watch stuff like this, is because they always have a little something that I didn't know about.
If I spin this one in this direction, precession.
See, that's wild. Is like that one spinning tire is enough to hold up both of them. Like that and he just gave it like one rack with his own hands. Like that's all. Like he didn't need like a power drill to get it going up to speed or anything. Like this, it is just wild. I don't know.
If in addition I spin the second one in the same direction,
like, am I the only one surprised that it just takes one try for him to get it to work properly?
two spinning wheels behaving
I
as
gotta
one.
try this myself. That's what I'm doing. That's what I'm doing after this. I have a bike. I could do this.
However,
Yeah, obviously now he's gonna do one in one direction, one in the other direction, and they're gonna cancel out. We all know that. Isn't it so fun watching this?
if I spin this one in this direction, and as nearly equally as I can, this one in the opposite direction, two spinning wheels behaving as if neither were spinning.
Yeah, there you go. I feel like he did this on purpose to get the people watching to make their guesses so that they would be right. Like, this is something that you do to encourage your audience to continue paying attention, is to give them all sorts of problems to solve and then make them feel smart when they get the obvious right answer.
And yet when I remove the canceling angular momentum, precession, as before. These two angular momenta seem to add, and they certainly did cancel. But we had a special case here. Both of the vectors were along the same straight line, so we have to carry our test a bit farther.
Well, this is going to be interesting. Now we're going to have like off-axis wheels spinning. Oh, that's exactly what this is.
On the table, we have an apparatus which consists of 3 motor-driven gyroscopes, each with a separate control unit. The 3 gyroscopes are mounted on an unbalanced plastic plate, free to rotate.
Yeah, this is an example I've never seen before. So I don't know what's going to happen. So this would be fun, me trying to guess what actually will be the result.
About this pivot and free to fall. What I'd like to do is to see whether the 3 angular momenta can be made to add to 0, in spite of the fact that they are not in the same straight line. In order to do this, I'd like to try to add this angular momentum to this angular momentum and see whether the middle angular momentum can cancel the other 2. So let's start the outer ones.
Before he even starts, I'm struggling to figure out like how this device even works. Like, what is going to be the way of illustrating that they're spinning properly?
First starting this one in this direction, angular momentum that way. And now this one in this direction, angular momentum that way.
Okay, so they're all pushing out. So he's going to try to spin the other one, but I don't know how they're going to illustrate it. He's going to spin the one in the middle to cancel out the angular momentum of the other 2, but it's just not going to move, right? Like, that's just, nothing's going to happen. I don't know. I don't know what's going to happen when that happens.
And while they're coming up to speed, let me remind you of something. The angular momentum of a gyroscope is directly proportional to its angular velocity. So that if I measure the angular velocity of a gyroscope, I'm measuring the angular momentum as well in some arbitrary unit. In addition, these 3 gyroscopes have been carefully made so that their moments of inertia are equal. This being the case, if I measure the angular velocities of these 3 gyroscopes, I am measuring their angular momentum.
Again, it's just staying in place, though. This is a lot less interesting to watch than the bicycle tires, but we'll keep watching.
As well in the same arbitrary unit. It's coming very close to being at the speed I'd like to have it. Let's try something.
That's cool, I guess. This is kind of like an airplane.
There.
I guess it's the same thing as the tire, just it's oriented differently.
Now, what have we? Let's go to the meters and see. Meter number 1, which reads the angular velocity of the first gyroscope, reads 5,000 revolutions per minute. Let's call that 5 arbitrary angular momentum units. Meter number 3, which reads the angular velocity of the third gyroscope, reads 5,000 revolutions per minute. Also 5 arbitrary angular momentum units, whereas the second gyroscope isn't turning at all. Now that we have this information, let's analyze the situation. We'll represent
That was a great sound bite. I feel like that sound was like good for a song or something.
Now that we have this information, let's analyze the situation.
Now that we have this information, let's analyze the situation. I like that. That just feels like something that would be put at like the end of a weird song or something, you know? That's a good sound bite. I don't know what the use of that sound bite is, but somebody take it and use it for something.
We'll represent the angular momentum of the first gyroscope by this vector and label it.
Is this a colored pencil? Is he writing in like, I don't know, forest green or something
L
and we just
equal
can't tell?
5 arbitrary angular momentum units. Of course, gyroscope number 3, having the same number of arbitrary angular momentum units, will also be represented by a vector of the same length, but in this direction.
See, I hope you guys are taking notes, right? You're copying all this down too? Good. When I walk around later, I better see this in all of your books, all right?
This angle has been chosen conveniently.
Okay, so he's going to make it spin in the opposite direction, the opposite rotation, and he's going to make it spin twice as fast. So he's going to get 2 angular units, whatever they are. He's going to get 10 in the opposite direction to cancel them all out.
So that these vectors will resolve.
Yeah, I know what 5 plus 5 is. I can do math. I'm pretty good at this.
By a 3, 4, 5 triangle. I'll resolve the first. 3 units in this direction. And 4 here.
Is that true? I thought they would add up to 5, but I guess like, yeah, triangles, like hypotenuse. I guess that makes sense. Isn't 3, 4, 5, isn't that like one of the perfect triangle squares or
I've
something?
now replaced this vector by its components, and the same for the second vector.
Dude, I love how unneat his writing is though. Like this is a true like presentation.
4, 3. These 2 vectors, pointing in opposite directions and of the same magnitude, of course, cancel. Leaving only.
Oh, so he's not going to do 10. Wow. I literally just said that I'm capable of doing math. So he's going to do 8 in the other direction, actually, not 10.
Only these 2 to be added.
I was totally messing up my vectors. That's the problem. Oh.
4 plus 4 in the same direction give a resultant of.
Dude, this is actually what my notes in high school looked like. Like that thick line. Like you can't, like nobody can even understand what's happening here anymore, but like it all makes sense in the moment.
8. So, angular momentum 1 plus angular momentum 3 adds to 8 units of angular momentum. 5 plus 5 giving 8.
5 plus 5 giving 8, of course.
In order to cancel the angular momentum contributed by gyroscope 1 and gyroscope.
But here's the thing. He's going to turn on that middle engine or whatever, and it's just going to stop working, right? It's just like, that's just not a very rewarding, like, end goal, you know?
3. Gyroscope 2 must provide an angular momentum of 8 units in the opposite direction. And in this way, an angular momentum of 5 plus an angular momentum of 5 plus an angular momentum of 8 will add to 0. Our vector analysis has shown that the angular momentum of gyroscopes 1 and 3 add to 8 units of angular momentum in this direction. In order to cancel these, gyroscope 2 will have to supply 8 units of angular momentum in this direction. Let's start gyroscope 2.
Dude, this push-in shot. See, that's the thing. Is like all of this was pretty much shot on like one camera, it looks like. But to get this shot, they obviously must have cut and then brought the camera in closer. It's just funny how 99% of this is an uncut, like just straight off the dome presentation. But then there are like shots within this where they actually get up close. It's just, again, I'm wondering about the process of making this. Like, did they film this all chronologically? Like, are they filming this now, right after he just gave that explanation? Or did they film this, like, way after the fact and they're just putting the footage in? It makes more sense for them to just do it all chronologically. I feel like that's how they would have done stuff like this back in the day. It just doesn't make sense to pause the whole presentation just so that you can get a shot of this when you can just get that same shot later, you know?
And watch it as it comes up to speed. 3,000 RPM, that is. 4,000. 5,000.
So yeah, once it gets to 8,000, it's just gonna like stop spinning and like drop down, right? It's not like nothing more amazing is going to happen. I don't think so anyway. That's my guess. Again, we're in uncharted territory, so this is just my intuition that I'm trying
6,000.
to explore.
7,000, 8,000.
Oh, right there. See, it stopped cold in its tracks. How did I know that was going to happen?
Is the angular momentum really gone from these three gyroscopes?
Yeah, see, but that's not as fun as the bike wheels because, like, now just nothing's happening. Like, it obviously gets the point across, and that's just not as satisfying. Like, it's just, oh, like, we figured it out, and now nothing happens. It's not as satisfying as a lesson as the first one, but it's still, I feel like we're more advanced now. Like, that first lesson was, like, yeah, intro to angular momentum. This is, like, the second lecture. This is, like, complex multi-axis angular momentum that we're dealing with now, which I guess is more complicated, so the examples aren't going to be as fun, but this was a little anticlimactic to solve.
It appears to be. Let's try something else now. Let's get rid of the angular momentum contributed by 1 and 3. Gyroscope 2 is now providing 8 units of angular momentum in this direction, whereas before 1 and 3 combined were providing 8 units of angular momentum in this direction.
See, but this is the part that I don't understand. It's like, why is this whole thing standing up? I don't know. Angular momentum is one of those things that just like ties your brain in a knot. Because it's spinning this way, so the momentum is going like laterally. So I don't know why the whole thing is getting lifted up. It's only sitting down because the weight of the actual spinning thing is weighing it down. So once it's spinning, that weight is kind of like lifted, I guess. And that's probably why it all lifts up. I don't know. Does that make sense? Am I figuring it out, or am I just revealing how dumb I am?
The angular momentum behaves.
Am I the only one still being amazed by this? Is everyone else watching just thinking this is like the most normal physics lesson ever?
Like a vector. We'll treat it as a vector. So now we can write in vector form L1 plus L3 plus L2 equals 0. Now that we have an angular momentum vector, let's pause for a moment and see how the angular momentum vector is changed. Let's go back to the disk again, rotating about an axis. If I want to change this angular momentum, I apply a force. At some distance from the axis, r. The torque that this force causes, T, is equal to the perpendicular component of the force, that is the force perpendicular to this radius, r, times the radius. So if the force were applied at half the distance, just as in the case of a lever, we'd need twice the force to cause the same effect. The torque causes a change in angular momentum, and the relationship between the torque and the change in angular momentum it causes.
Yeah, I'm sorry. My eyes kind of just glazed over for a minute. We're just looking at a piece of paper with equations on it. This is like, I hope I'm giving you all flashbacks to high school right now, because that's what I just went through.
The torque times the time for which it's applied is equal to...
It's hard. It's hard sometimes to just pay attention to a guy writing on a piece of paper physics equations. It's not even in color, you know? Like, it's hard to just not get bored watching this sometimes.
to the change of angular momentum it causes.
Yeah, I'm not following anymore at all either.
But angular momentum is a vector, so the change of angular momentum is a vector. And we expect this to be a vector equation. There's no vector nature in the time, and so the torque must be a vector. We know its magnitude, and now we have to find out about its direction. We define the direction of the torque in the same way as we did for the angular momentum, using a right-hand rule, as follows. If the
Oh man, we're getting the right-hand rule again.
fingers of the right hand are made to point along the direction of the force applied, then the thumb of the right hand points out the direction of the torque.
The direction of the torque? Really? So the torque, I thought that was the angular momentum. Is that different?
You see, this rule is good whether we apply the force here, closer to the axis, at this point on the wheel, in fact, at any point on the wheel. And you see that it does indeed work here, because this force applied in this way would cause an increase in the angular momentum of this wheel in this direction. The torque in this direction causes an increase in angular momentum in this direction. But we chose a particularly simple direction.
Dude, and I also love that this whole time he has had these gyros going on in the background, making this like drilling noise, or this droning noise, I guess. Like, and again, this is all like, it's all live. He forgot to turn them off, or he wasn't even supposed to turn them off. I guess they just did not. They weren't thinking about the audio quality when they were setting up this experiment, I guess. It's just tough because all I've been looking at this, like, for the past, like, 4 minutes, is just this piece of paper.
For applying this force. We might have applied it this way, or this way. In any case, the same rule applies. And now we're in a position to begin to understand...
You know, I bet there are YouTube videos out there that try to explain this same exact thing. I don't know if I've ever watched any, like, physics YouTube content, but I bet there is somebody who has this same exact lesson. I wonder if this is better or worse, though. It must be so hard to illustrate physics is the thing. Like, you know, you have to show, like, forces and whatever. Like, there's no, like real physical, tangible way to illustrate a lot of this stuff. So, I guess I get it. I get why the visuals are kind of lacking at the moment, but my understanding of it doesn't affect the fact that I'm getting a little bored.
the precession of a gyroscope.
Like, it actually is starting to feel like I'm in school. Like, I am ready to take this test. Actually, that's probably not true.
Here we have a gyroscope, very well balanced and mounted on gimbals. The gimbals permit the gyroscope to turn in any direction and in any position assure that there'll be no torque acting on it. Let's put some angular momentum in this gyroscope.
Oh, see, now he's not doing it by hand. Now he has a little electrical instrument to spin this thing up. That's funny. Again, we just watched like 10 or 15 uninterrupted seconds of him doing nothing but holding up this spinning device to this thing, which is like, you could have just cut this out also and it would have been fine. We would have understood. But no, we have to watch him bring it up to speed. We have to watch it achieve like 5,000 RPM in real time. All right, somebody count how long we just watched that one whole clip for.
The wheel was turning this way, so the angular momentum vector points toward you. What would happen if I pulled down at this point? Let's try it in...
If you pulled down? I feel like if you pull it down, it's going to want to right itself. It's just going to want to go back into that position.
See. I'll use a kilogram.
Oh, it starts to spin precessionally? Interesting. That's weird. Why does it do that? I never would have guessed that.
Now that we've seen it, let's explain it. The wheel was turning in this direction so that the angular momentum was pointed out here toward you. we applied a force downward at this point, which caused a torque in this direction. A torque in this direction.
Oh, okay. All right, that's interesting. So it's like two different angular momentums taking place, you know? Like the actual movement of the whole gyro turning like that created its own angular momentum that then turns it that way. That's interesting. See, again, this is like such a complex mechanism that we're dealing with right here. I feel like I'm not that embarrassed that I got that wrong. To be fair, it did not move in any other way that I expected. I didn't expect it to move that way, but I also didn't expect it to move up and down. So, partial credit, I'll say.
So, we had the original angular momentum pointed outward toward you, plus a change in angular momentum, which gives the new angular momentum along the shaft. The old vector, plus the change in the vector, which gives the new vector. In fact, a good way to remember this is to think of it this way, that the motion of the angular momentum vector is such as to tend to align it with the torque vector.
I'm going to try to think about what he just said, but I don't know if that made any sense to me.
Let's see that again.
Yes, please, let's see it
now,
again.
And again, but now.
It's just so funny. He does it so briefly because it can only go for so long before it stops. I don't actually think I understand it. Like, I think I get why, but I would never anticipate this happening.
If I apply the force continuously, there's a continuous torque.
Yeah, I don't get it.
A continuous torque makes a continuous change in angular momentum. And we have precession. It can also be shown that the rate of this precession depends on only two quantities, the angular momentum of the wheel.
Thing, I just realized, though, that this thing is still spinning. Like, he hasn't respun it or anything. Like, it's just going. I guess that's why we had to watch him spin it up for so long.
Now that we've seen how precession takes place, let's try to predict its direction in this case. I'll spin this wheel in this direction. And so the angular momentum of the wheel will be pointed along the shaft in this way. The torque will be supplied by the force of gravity downward here and the force of the pivot acting on the shaft upward here, so that the torque will be in this direction.
I'm trying to think about that. Okay, so yeah, the pole is providing a force up, gravity is providing a force down. But do those cancel out? I don't know. Oh, but it wants to spin. Okay, yeah, I had to be looking at it by the side to actually understand. So this thing wants to drop that way, so then it's going to be pushing out that way, so it's gonna spin counterclockwise is my guess. I know we already watched this, but I didn't remember which direction things rotated. Let's see if it's right though. If it goes counterclockwise, I'll consider this whole thing a win if it goes counterclockwise.
This way or this way?
If not, I'm gonna watch this whole thing over again.
Can you tell? Try it.
It's going counterclockwise. It's going to go the other way.
Are you ready?
I'm freaking ready. Dang, I just got it wrong. Oh, no. Oh, my God. Oh, my God. I really thought I was going to be right, too. All right, let me try to figure this out. Hang on. So it's trying to rotate that way. Well, now it makes sense. I don't know. Did I just get it wrong? Did I make a dumb mistake? It makes sense now. Because it's rotating, it's going to come this way. Why did I get it wrong? Oh, I'm doing it with my left hand. That's why. It's the right hand rule. Oh, my gosh. Dude, is this it? Is this the outro? Just it spinning? That's actually a bold-ass outro. Like, you just know that this guy is just hanging out off to the side of the camera right now, you know? Oh, that was it. Oh, okay. Experimental Assistance by George Fardy. Was this guy George Fardy? Because Experimental Assistance, I can only imagine it was him. I feel like he would get a different credit, though. Like, the presenter would get a different credit than the Experimental Assistance. So this guy probably isn't George Fardy. Okay, let's see. Directed by John Friedman, edited, sound recorded by unit producer Graphic Arts. So they're not actually going to say who the guy is? Oh, okay, so executive producer Kevin Smith. No way, Kevin Smith made this? And then staff physicist James Strickland. Is this guy the staff physicist? Again, that's a weird title to give to him? Or was he just like a paid actor and James Strickland, this staff physicist, was like the guy who actually set up all these examples? I don't know. I'm just curious. Yeah, but that's the end of it though. Okay, so my big question at the end of all of this is if something spins and it generates angular momentum, then if you spin something around horizontally, shouldn't it be providing a upward momentum or an upward, vector, I guess, right? Like if something's spinning like this, the momentum's going up. So shouldn't you be able to like fly? I know it's like it might be like a infinite energy machine where it's like it's impossible to get something going fast enough where its angular momentum exceeds its like a gravitational pull, but it just seems like to me, like if you can make a force like that going around, then like you can have things spinning and lifting up at the same time. Are you guys following me? Does that make sense? Like, I don't know. The reason I thought about this is because of like flying saucers. They always look like they spin, right? They always look like they spin really fast. Every shape of a flying saucer ever has been purely circular. And my thought is that like, I don't know, this is going to sound crazy, but like any flying device that's perfectly circular is probably somehow taking advantage of like angular momentum. Like I think if you made a flying saucer and you put something inside of this flying saucer to spin so fast that you could actually get like upward movement. That's my question. That is the thing that I have been curious about for angular momentum. That's the question that I wanted to ask my 8th grade science teacher about this that I just never got to because I was too scared to say that in front of the whole class. But can somebody explain that to me? In the comments, take the time. I don't care what you do, and I'll read it. I'll read it for sure. And explain to me if that's possible or if you can never spin fast enough to actually lift the mass that's spinning. Because I don't think that is necessarily true. I just think that you could create something that flies by having it spin so fast. And I have never heard a reason why you can't make something like that. And all the UFO flying saucer stuff, like, I really have been thinking about this a lot lately, especially, but I want to know that. Can you create something that spins so fast that the angular momentum picks it off the floor? I want to know that. I want to know if that's possible, and if so, can I patent that? So you guys work on that. That's actually the homework, right? I'm the teacher. That's the homework for today. So go home, think about this some more. Can you get something to fly just by spinning it around? Based on what I've learned, it seems like that is possible. But again, I don't know, but that's my big question. So let me know, and I guess we're just going to cut to black.